Okay, so simple enough equation on the face of it. Find all the integers n where sigma n is equal to 12. And you'll recall what the plot of the function looked like. Recall the plot of phi. I mean, I could bring it up, and I probably should bring it up on the computer. But remember, it was a cloud of dots. Remember this kind of picture I was showing you for the plot of the Euler phi function? It was this kind of fan of dots fanning out from the origin. So somewhere here we have 12, and so maybe there are some number of dots along that line, some number of integers where 5n is 12. Now it was very suggestive when we plotted the scatter plot of the values of the function that it was fanning out. So for any particular value, just from observing what's going on with the plot, for any particular value, we might only expect just a finite number of solutions, a finite number of numbers where 5n is 12. Okay? So remember, we expect at most a finite number of solutions. Finite number of n, just from the graph. Okay, it's no kind of proof. Well, I mean, it's a suggestive argument. It's certainly not a proof of it. I mean, how do we know that far out here the numbers, the dots don't start coming down again, so to speak? It's fine. Okay, so how are we going to answer this question? Well, this requires, this requires the application of the previous results, okay? So the application of mainly two things. The application of one, the fundamental theorem of arithmetic, the FTA, okay? Which says that every integer factors uniquely into a product of prime numbers, okay? So it gives you a way to systematically talk about the integers. And two, the multiplicative formula for phi. Okay. In light of some of the comments in the feedback survey we did last week, which I'll be giving you, I'm just preparing a summary of them and some comments on them, which I'll have ready for tomorrow's lecture. But one of the requests that comes up sometimes is looking for more examples and applications. So, I just want to stress that these are here and point out areas where they're coming up. Okay, so we're very much going to see an application of the fundamental theorem of arithmetic here and the multiplicative formula for phi. Okay, so at the moment we're looking for these n. Okay, so you think of n as, thanks to the fundamental theorem of arithmetic, this is what an n looks like. Okay, that's a typical prime factorization. You've got some number r of primes, p1, p2, p3, up to pr, and they appear raised to various powers, alpha 1, alpha 2, up to alpha r. Okay, so this, at the moment, this could be any integer n, any positive integer n. Okay. Now we're trying to solve phi of n equals 12, so we apply the multiplicative formula, and you should be almost able to do that in your sleep now. That's the multiplicative formula, and we put an equals 12 at the end of it, and then we solve it. Okay, so it looks even easier now. Just solve that equation. Solve it for n. But you see what, on the one hand, you think of n as just a simple single variable representing a number, but actually, when we're thinking of it in terms of its prime factorization, there's a lot of richness and structure there. Okay? So some number r of the number of prime factors it has. Okay? There's the actual values, pi of those primes, which primes are involved, the number of primes, which of them are, and the values of these exponents. So how frequently does each of these primes occur in the prime factorization of n? So from suddenly looking at n as just being a single parameter thing, n is some value. But now we see we've at least got the individual pi, there's r of them. So there's one, r plus 1, and then another r, the exponent. So it's something like 2r plus 1, cloud parameters there defining it. And somehow we got to marshal them all and figure out the possibilities for them all when it's equal to 12. Okay, so does this, or surely this must place some restrictions. So what restrictions does this place on n? This is the question we're going to have to deal with to make progress. You can see from the graph, and if I could run the computer, we could run the computer, we could actually solve it and find these values first. But we're trying to understand it, And if we can solve it for 5n equals 12, then in principle we would understand the solution method and be able to think of solving it for any number, 5n equals whatever. So we don't just want to go to ask the computer what the answer is. We'll ask it to double check when we've got our solutions. Well, we expect, that the feeling is, just from looking at the graph, that there's a smallish number of smallish n's that are solving. Okay? So why is that? What kind of information can we start to get out from looking at this equation? I'm not necessarily looking for the solutions n to come out at this stage, but are we getting any information about anything in the prime factorization of n from this? So at the moment, n could be any positive integer because we haven't put any restrictions on the number of primes, on the primes themselves, or on the values of their exponents. Okay.
The lowest integer is going to be 13.
The lowest, so you're saying all of these primes are less than 13, is what you're saying?
No, I'm saying all bigger. All of the integers are bigger than 13. Is what I'm saying. As in all of the n's.
Okay, all the n are bigger than 13. Yeah. So all the n satisfy n bigger than or equal to 13. Yeah, that makes sense. Why?
Because 13 is prime, so x5 is going to be 1 less than 13.
Just 12, yeah.
I know.
Okay, well, what you've said, from what you've said already, we've already spotted one of the solutions, 13. 5, 13 is 12. And I think what you're saying, think of the definition of phi. Phi is the number of integers in the range 1 to n that are co-prime to n. Okay? So it's some subset of the numbers between 1 and n. So if you want it to be 12, there has to be at least 12 numbers there, isn't there, in the range 1 to n. Yeah. 5n only counts some of the integers less than n, just the ones that are co-prime to n. So if you want to count, if you want there to be 12 integers less than n that are co-prime to n, there must be at least 12 of them there to begin with. Okay? So your n must be at least 13. And 13 happens to be an actual solution. See, maybe we should think about, since we've got so many prime factorizations on the page, we should think about 12 and its prime factorization. Which is 2 squared by 3. Does that help us? Does that help us any? Or? So what are the primes pi that might occur? That might occur in n. We've already identified p as being 13. 13 might appear in the prime factorization of n. Okay. Have you any other suggestions for primes that might appear? Or can you tell me a prime that you know definitely won't appear? Maybe we can answer it in the negative. Is there a prime that you know will not appear in n? So you imagine primes up here appearing in n, but then they make an appearance down here in phi of n. Yeah? So anybody name me a prime that does not appear in n if phi of n is going to be 12?
Any prime greater than 12.
Any prime greater than 12? Yeah. So if you did have a prime greater than 12, it would pop up one less than it there.
Except 30.
Except, well, yeah, 13 we've already found. So any prime strictly bigger than 13. Yeah. Your thought is right. Yeah, because any big prime generates a more or less equally big factor here, which will, in a product, will make it larger than 12. Yeah. So the primes can't be too big. They must. So all these p must be less than or equal to 13. Well, that is an amazing progress, because up here, that's amazing progress because up at this stage there was an infinite number of primes to choose from. Up here there was an infinite number of primes that might have made an appearance in it. Now there's only a handful. Yeah, so that's excellent. So the possibilities now for p, well, let's just put down all the primes less than 13. That you should be able to do in your sleep. Except 8, 9, 10, 11, 13. Might all of those occur in the prime factorization of n?
No.
So why not?
Well, you can have to have some combinations of multiply together to make 12. And some of them aren't going to.
Multiply together in this way.
Yeah.
Okay.
So like if, say, 11 was one of them, you're going to have 11 minus 1, which would be 10. But 10 times by none of them is a minus 1. So.
Excellent. So 11 is not allowed. Because 11 minus 1 equals 10, and that's going to have to be sitting here in a product that's equal to 12. Well, that's impossible. It's impossible because it's got a 5 in it, doesn't it? 5 is a prime dividing 10, but 5 does not divide 12. We don't see it in the prime factorization over here. So all these times, in these occasions, we're kind of using the prime factor, the fundamental theorem of arithmetic, kind of, to justify it. So 5 divides 10, but 5 does not divide 12, because 12 is 2 2s and 3. So 11 is disqualified from appearing. But just individual, okay, so probably not all of them multiplied together, so that's going to generate something pretty large when you fit it into this formula. But just individually, like, might the 2 appear? Well, yeah, the 2 will generate a fact, maybe some factors of 2 here, maybe a 1. That's divisible. That's factors of 12. Might the 3 appear? Yeah, it could generate another 3 here, and it could generate a 2 here, but those are factors of 12. So the 3 can make an appearance. Might 5 appear? Maybe. We can't allow it to survive here, so it must only be 5 to the power 1. Yeah? And the 5 minus 1 would generate a 4, which we do see here. Yeah. The 7, again, we shouldn't allow it to survive here. But 7 minus 1 will give us a 6, which is a 2 by 3, which we do see in 12. And the 13, well, we shouldn't allow it to survive in the powers of 13, but it will generate a 12, which will be okay. So individually, each of these 1, 2, 3, 4, 5 primes might make an appearance. So this is great progress. From an infinite list of primes to choose from, we've now boiled it down to some combinations of these 5. Okay. Yeah. And we've already identified one of the solutions, and maybe identified another few of them there in just what I was explaining there. But we want to be very careful and be very systematic and make sure we capture all of the solutions and that we don't miss any out. So we'll try and approach it systematically. So lots of solutions appearing to us here, or we're starting to see them through the mist. But let's be sure, let's work systematically to be sure to capture them all, because it's very easy in this case that when you start to see solutions leak out of your argument page, you just start picking them up one by one and having a look around, seeing the solutions, but then you might go away then with a bunch of solutions, but you might have left some behind. Okay, so you just want to be careful not to do that. Yeah. See, everything's been quite rigorous up to here. We've had rigorous arguments as otherwise. See, the prime has to be less than 13, as otherwise 5n would be greater than 12. We've had very rigorous arguments up to now, so we just want to keep that going. Okay. So the solutions n must be of the form, well, we look at its prime factorization. So we did have a completely general prime factorization up here, but now we know it's a bit easier. It's some 2's by some 3's by some 5's by some 7's by some 13's. And these might have various exponents. I'm going to label these exponents A, B, C, D, E. So I'm not calling them alpha 1, alpha 2, because there's only a small number of them. And it may be easy to work with. A, B, C, D, E. So these are our n's. Now, I'm by no means claiming that they're all solutions. And they're not. But we can start to put, see, now we've got the restrictions on the primes. Now you think about restrictions on the exponents. See, up here, the exponents were any positive integers in your general factorization. So naively, these exponents might be any positive values, but surely they can't be. We want 5n to be equal to 12. So what are some restrictions? That must be the case. Sorry?
What did you add at the top?
On that you can see now? Here?
No, just add something.
I added something. Oh, sorry. It was the alpha I were strictly positive. That's the default position for these exponents, prime factorization of n. But we now know a lot about this n. We need 5n to be 12. So restrictions on these exponents.
The CDs and E's are never going to be what?
C, D, and E less than or equal to 1. So why is that?
Because in the multiplicative formula, it has a section of sorry, 2 nil. Because we didn't want them to survive outside of that.
Yeah.
Yeah, so what?
So there are no, so 5, 7, and 13, there are no factors of 5, 7, or 13 and 12. So we can't let them survive, as we speak. So by surviving, I mean that there's still a factor of 5, 7, or 13 here. So the way to have them not survive is to not let them have an exponent of greater than 1. Because if their exponent is only 1, then when you fit them into this formula, you then got 5 to the power 0, 7 to the power 0, 13 to the power 0. So they don't really make an appearance there. Yeah, okay. And of course, they might be bigger than or equal to 0. So really for C, D, and E, there's only 2 options for each of them individually, 0 or 1. Yeah. Any other restrictions at this stage? Similar thinking to that. Just extend it to the other prime, to the 2s and 3s. Could I have any value for A and any value for B in here?
A must be like less than or equal to 3.
A less than or equal to 3. Yeah, because if you had 2 to the 4 inside n, you'd have 2 to the 3 generated here, which is 8, which is not a factor of 12. Yeah. So 2 to the 3 is as far as you can go. Yeah, I've said 2 to the 3. Yeah, that's correct. So 0 must be less than or equal to A, must be less than or equal to 3. And what about the 3, the B's? Surely we can get some restriction on those. Yeah, Francesca, same but 2. Yeah. Yeah. Okay. 3. We can have a 3 squared. That would generate a 3 here, and we see a factor of 3. We'd also generate a 2, but that's okay. We do see some 2s. But we couldn't have a 3 cubed, because 3 cubed up there would generate 3 squared here, which is 9, which is too much for the 12 to handle. Yeah. So look how much progress we've made. We've gone from an infinite number of possibilities of n down to how many possibilities have we got here? How many possible? How big is the field of possible solutions now? Well, you see, any n, it just comes down to the number of different choices for these exponents. C, D, and E, there's 2 choices each. A, there's 4, and B, there's 3. So it's 2 by 2 by 2, which is 8, by 3, which is 24, by 4, which is whatever it is, 96. 24 by 4, 96. 96. So there's still 96 different possible ends that we've got on the page. So still quite a lot. So we still have to be very careful that we identify them all, and that we don't leave any behind, because 96 is still a fair collection. Okay, but this is good. Excellent progress. Okay, all the other infinite amount of integers we've excluded. Okay. So even already you can see the power of the fundamental theorem of arithmetic. Just this principle that every integer factors uniquely into primes. It's uniquely that's important here, because here's a 12 with its two 2's and a 3, and we know that then any other prime factors in n that generate anything else in here that isn't contained in here must be excluded as a possibility. Okay, so that's the power of it. Okay, so now we need a case-by-case analysis. I think we've gone as far as we can looking at each prime individually. We now need to start thinking about all 96 of these possibilities. We now need a case-by-case analysis. Well, we either start at the bottom or the top. We've already actually identified one of the solutions as 13, so I'd say we start at the top. Get rid of the big, the big numbers maybe I don't know. There's more I mean, there's certainly more flexibility with the A's and B's. So maybe try and get rid of some of the easier cases first. So let's suppose E was equal to 1. So that would mean N is equal to 13 times something, 13 times an M. So the M is whatever the rest of it that it has. So in other words, the M, the complementary factor to 13, is going to be co-prime to 13. And here's an application of another property of the phi function, the multiplicative. Well, it's all associated together, of course, but the multiplicative nature of phi. So phi of n here is going to be phi of 13 times n. But these are co-prime, so this can split up now. It's phi of 13 times phi of n, which is equal to 12 times phi of m. But remember, this thing is supposed to be equal to 12. So now we know a lot about the m, i.e. phi of m is equal to 1. What does that tell us? So see, what we're trying to figure out here is if the exponent on 13 was 1, what other possibilities are there? So the other possibilities are bundled up in this m. And this m has to satisfy phi of m is equal to 1. So which numbers have a phi value equal to 1? Say that again?
2.
What are they?
No, I think the number 2.
The number 2. Ah, okay. I thought you were saying there were 2 numbers.
And the number 1.
And the number 1. So you were right both ways. So there's only two numbers with phi of m equals 1. And if you think about it, the definition of phi is the number of numbers between 1 and m that are co-prime to m. So if m is equal to 1, 1 is co-prime to itself. If m is equal to 2, of the numbers 1 and 2, only 1 is co-prime to 2. So phi of 2 is equal to 1. Once you get any higher, just to prove that, the proof that there's no other m, if m is greater than or equal to 3, then the GCD of 1 and m is equal to the GCD of m minus 1 with m. These at least are both co-prime to m. If some number bigger than 3 or bigger, you've at least got 1 and 1 less than the m that are going to be co-prime to m. That's at least 2. Okay. So we have solutions. 13m, and only 2 possibilities for m. M is 1 or 2. Yeah? So n equal to 13 and 26. Okay, so that's 2 numbers out of these 96 possibilities. Yeah, that's good. But that's the only solutions with e equals 1. So otherwise, e equals 0. So we can forget about the 13s. We've dealt with all the cases where 13 plays a role. So we should come down to the 7th, shouldn't we? Possibilities for d are 0 and 1. So suppose d equals 1. And there's no 13s either. So in that case, our n is equal to 7 times m, where the GCD of m and 7 is 1. So the m is all the rest of n, whatever the 2, 3, and 5s are doing. Yeah, that's gathered together in n, but it's 2s, 3s, and 5s, there's no 7, so it is co-prime to 7. So again, 5n will be equal to 5, 7 times 5m. Oh, I never referenced that up here. So this step here is using the multiplicative multiplicative nature of phi. Okay, so it's very useful. So we're using it again here. So it's phi multiplicative. Well, we know what 5, 7 is. 7 is just a single prime. This is equal to 6 times 5m. And this is supposed to be equal to 12, so that implies 5m is equal to 2. So which numbers of 5m equals 2? So we're going to have to solve these smaller examples of the problems. Well, if 5m was 2, see 2, the prime factorization of 2 is just 2. So you think of all the m's you could have and their associated 5m values. If it's just going to be equal to 2, okay, only the primes 2 and 3 might make an appearance. If 3 makes an appearance, it must be to the power 1, because the 3 can't survive, and the 3 will generate the 2. So m equals 3 is a possibility. Also, m equals 6, you could have the 2 multiplied by 3. So m could be 2 by 3, because then in the 5m you'd have 1 by 2 by 1 by 1. Yeah, so you'd still have 2. And also m equals 4. If you had 2 squared, then the phi value would just be 2 to the power 1 by 1. So it would still be 2. So the only possibilities are 3, 4, and 6. Okay? I mean, proof for that, well, we can only have 2 dividing m and 3 dividing m. Right? Since any other prime divisor would generate something bigger than 2 in the phi value, and any higher exponents on them than 1, 2 2s and no 3s and 1 2 and 1 3. Any higher exponents, you just look at the phi formula, it's going to give you a value much bigger than 2. Okay, because you have more factors in there. Any higher exponents will give phi of m being bigger than 2. So, but this is another 3 solutions. So n is 7 times m is 3, 4, and 6. So we have 3 more solutions, n equal to 21, 28, and 42. Bingo. So the 96 are falling quickly. Okay. We've gathered up, how many solutions have we got so far? 2, 5, 13, 26, and these 3. But otherwise D must be 0, yeah? Because the only possibilities up for it were 1 and 0. We dealt with the case 1, so now we assume it's 0. Okay. So now our n is looking like, what does the n look like now? It's just 2 3s and 5s. I guess we look at, just keep going, same thing. Suppose C is 1. And there's no 7s and no 13s. We've already dealt with those cases. So same thing. N is equal to 5 by m. The m has the 2s and 3s if there are any. So that's co-prime to 5. So 5n, exactly the same analysis as phi of m, 5 times phi of m, which is 4 times 5m. This is supposed to be equal to 12, so that implies 5m is 3. 5m equals 3. So m is a product of a load of things like that. 5m multiplicative formula is a product of a load of things like that. Okay? I just use q's to differentiate it from the version I wrote for n before. Q's are our alternative letter for primes, remember in number theory? P's and q's shouldn't really be used for anything else apart from primes in number theory. So does 5m, which n's give you 5m equals 3? How can an expression like this here be equal to 3? Well, you first you think, well, surely almost all the primes can't appear. There's only a small possible number of primes. Think about, well, for any prime that you admit into M, it's going to generate a factor q minus 1. See every prime number, q minus 1, every prime number q minus 1 is never equal to 3. Yeah? Because it would have to be q, would have to be 4. 4 is not a prime. Okay. So you never get a factor 3 out of the q minus 1. The only way to obtain the factor 3 is to get it out of this power of q itself. Well, the only way you'll get a 3 surviving here is if you had 3 squared in m. But if you do have 3 squared in m, you're going to have a 3 here, but you're also going to get a 2 there. So you're going to get 5. You're going to get at least a factor of 6 in 5. So that's kind of a proof that there are no m. There are no such m. There are no m. There are no such m. Yeah, because if you take it here, 5m equals 3 implies that we must have at least 3 squared dividing m. So that's the only way we can generate a 3. But then that implies that 6 divides 5m, which is a contradiction. So there can't be any of these m's. So you feel sad, you have to find solutions, but no, you feel happy because you've ruled out a case. Okay, C cannot be 1. Okay. So what this represents, so we've suddenly ruled out half of the 96 here. You see, remember there's 2 possibilities for C, 0 or 1, wasn't there? And if it can't be 1, we've ruled out what's half 48 of the possibilities. Okay, so no solutions here. That's excellent progress. Half of the 48 of them are gone. We've already ruled out probably some of those 48 already. But. So otherwise C is 0. And now our n is looking a lot simpler. It's 2 to the a, 3 to the b. But the a's and b's, there was the most flexibility there. What was the conditions? A was 0 through 2, and b was 0 through 1. So a is equal to 0, 1, 2, or 3. B is 0, 1, or 2. Not saying that these are just the possibilities. Yeah. I think we can go for it now. We can, when you get close enough to your goal, you can just make a final leap. Let's just deal with these two together. So 5n here, because we know the multiplicative formula. This is the prime factorization of n in this case. So it's going to be 2 to the a minus 1 times 3 to the b minus 1 times an extra 2. So in other words, 2 to the a times 3 to the b minus 1. Yeah? And this is supposed to be equal to 12. But we already know 12 is 2 squared by 3. Again, this is the prime fundamental theorem of arithmetic being used. Numbers have unique prime factorizations. So if 12 factors into primes this way, it's the only way to factor it into primes. So over here, you've got potentially another product of 2s and 3s, but it must be exactly this one. There's no other possibilities. That kind of feels obvious because we're down at the level of 12. Of course, you can only write 12 as 2 squared by 3. But when you get up into the realms of gigantic integers with many, many, many prime factors, that's a very useful property to have and in a general principle to have, that prime factorizations are unique. Okay? So anything looking like a product of primes over here and a potentially different product of primes, if they are the same in value, the two products must be essentially the same. The only flexibility is how you move the factors around on the page. It isn't really changing, is it? So this implies the A must be equal to 2, and the B minus 1 is 3, so the B is equal to, B minus 1 is 1, so the B is 2. Yep. A is 2 is B is 2. So one final solution. One last remaining solution. Boy, the phrase final solution. So what is this? This is 2 squared by 3 squared. 4 by 9, 36. Okay, excellent. Now, so we found solutions. Let's gather them all here. And they were in order. They were 13, 20, well, not quite in order. 21, 28, 42, and 36. 1, 2, 3, 4, 5. 6. 6 of the 96 possibilities. Good. Yeah. Are we confident we found all the solutions? 96 was a big step. But yeah, we can be confident because we worked extremely systematically. We boiled it down as much as possible. We restricted our n by just thinking of individual prime factors as much as possible. We got it down to a small collection of primes with a small number of possibilities for their exponents. But then we have to start thinking, well, how those individual possibilities come together. There's potentially 96 things to consider, but by passing through those 96 extremely systematically, we've just arrived at these solutions. Okay, just those solutions, and there aren't others. Okay, you can be gathering up your stuff, but let's just see a quick computer confirmation of that, just for our. Let's see if I can get it up in time. Doing that. Doing this. God. So what would we do if we wanted to demo this quickly? Well, what I'm going to do is write a quick little for loop that's going to just loop through the integers, say between 1 and 100, and just tell me all those ones that have phi value equal to 12. If I can wake this up. Wake up. Ah, there's our graphing. Excellent. Nice. Serendipitous. Okay, let's go. For n in the range 1 to, let's go, 1,000, just to be sure. If Euler, what's it called, phi of n is equal to 12, then I want to print n. And the bar stopped flashing, so it's finished. And yeah, it's just found those solutions, 13, 21, 26, 28, 26, and 42. Okay? So, well done. I'll see you again tomorrow afternoon. We'll do some more of this. Do some more of this stuff.